Thank you. So I'm here to talk about the work that we have been doing at AI Sweden on building the first large language model for the Nordic languages. And my guess is that this will not be the only presentation during today where the term large language model will be mentioned. So I'm going to take this opportunity to start this day by just aligning ourselves a little bit on the basics here. So when we talk about large language models, what we are aiming for is simply a statistical model that learns a probability distribution over language. And these models can learn that probability distribution by simply doing some form of predicting words in context, right? We can do this in several different ways. We can try to fill in the blanks, or we can do just simple next token prediction, or other variations of that. But the point in doing that is then that the model will learn a language distribution over the data, okay? And the point of learning a language distribution is that we can use that distribution either to derive representations for language, which we can then use, or we can simply sample from the language distribution and then produce language, right? So I am primarily going to talk about generative models that sample from the distribution. And I think that probably applies to most other presentations during the conference also. So it's worth keeping in mind that these generative models are built explicitly to play language games, right? I think this is a useful term because it points to the importance of providing adequate rules for the language games that we want the model to be able to play. So I mean, if you talk to a human counterpart, you wouldn't expect them to respond to you coherently unless you provide sufficient context to them. And the same applies to a language model, right? Okay, so I hope that this is all very obvious to you, but I think that just keeping this in mind might mitigate some of the misconceptions that we see in the current discussion about language models. Okay, so let's move on. Another thing I think is worth keeping in mind is that language models per se, as a technology, is not something new. We've been working on language models since the early days of language technology. But what is new is that we have the transformer architecture. So in 2017, Attention is All You Need came out, and in 2018, we started to see the first transformer-based language models. And by then, we were primarily focusing on encoder-type models, and this was really a disruptive event in language technology. So more or less overnight, we went from working with traditional NLP processing pipelines to then basing everything off of a transformer, pre-trained transformer language model. And of course, the point of doing that is that we can improve on the results by using a pre-trained language model, and we typically also need less training data for fine-tuning the model to various tasks. We were quite early adopters here in Sweden when it comes to language models. So the first Swedish encoder model was actually built by Felix Stollenberg, who was then at Arbetsförmedlingen, who's now part of our team at AI Sweden. And then, of course, we had all the Swedish encoders coming out from KB Lab. In 2019, we started a project called Language Models for Swedish Authorities with the idea of promoting the development and application of language models primarily in the public sector. And that was a successful project. But in the middle of that project, another disruption happened, which was GPT-3 was released in summer of 2020. And that sort of started a new trend where we saw people going from working with encoders to now working with decoder networks, so essentially going from BERT to GPT-like models, and also scaling up the model size. And the point of doing that is that we can arrive at a more general model that we can directly apply to tasks even without fine-tuning. So going directly from pre-training to application. So nowadays we don't only talk about language models, but we talk about large language models, right? And if you look at the development in the field of machine learning when it comes to parameter size, this is a nice graph that I found on some blog. You have the link down there. It shows the number of parameters of machine learning systems over time. And you see some nice linear trend going on there from the 50s onwards. And you also see, quite interestingly, different types of machine learning domains. So you have Blue is games, green is vision, yellow is other, which I guess is like bioinformatics and maybe recommendation systems. And then you have red, which is language. And that really takes off then in 2018. I thought that was because of the transformer, but now I heard that GAIA started in 2018. So this might be because of GAIA, no. But this is quite interesting, and some people talk about this as the large-scale era of machine learning that we have entered now. And if we zoom into just the language model part, and this is something that you are all very familiar with, this is the development over time or over models when it comes to language models, and these are dense transformer networks. So we had BERT coming out in 2018 with 100 million parameters, and the large one had 300 million parameters. GPT-2 over 1 billion parameters. GPT-3 175 billion parameters, and then the largest models that I am aware of right now, the Pathways language model with 540 billion parameters. Quite interestingly also, most of these are not open source, of course. They're closed source. So you have the blue model, which is, as far as I know, the biggest available model with 176 billion parameters. But it's not only the parameter size that is growing, it's also the data size. So we are now training on not only 100 billion tokens, where actually the models that are trained on most data are over 1 trillion tokens. So you have Chinchilla and you have the Llama models from Meta also. But so if you're interested in scaling, as we are in our group, there are sort of different directions going on. So either you scale up the model size, which is what people talked about when GPT-3 came out, and then you have sort of conflicting evidence, especially in the Hoffman paper from DeepMind, where they say, no, you should scale data instead. And then there has been a lot of other papers that sort of contribute to the confusion here, claiming either you scale model size and or data size. So it's not really obvious how you produce a large-scale model with general capacity. But of course, the point in building a large model, and this is an image that I stole from the Google blog where they introduced Palm, is that not only do the models become better when you scale them up, they also become more general. So you have some sort of general capacity model when you scale up the model size and the data size. And of course, these models also can be applied to tasks that are non-trivial and that we might thought just a couple of years ago were perhaps not possible to solve just using language models. And of course, these have sparked the recent discussions about whether these models actually understand language or if they only behave as if they understand language. And I find this discussion entertaining, and if you have a philosophical inclination, there are lots of interesting papers to read here with absolutely no practical consequence at all. But it's also interesting if you actually talk to people in the field, and this was a survey that was published last year, the NLP survey, where we talked to people in the field and asked them questions. And maybe some of you were part of this. If you ask people in the field, do language models understand language? About half of us reply yes to that. And if you then add multimodality, then even more of us would say that, yeah, they do really understand language. There was also a really interesting paper from Stanford, just I think it was a couple of weeks ago or something, where they show results on what is called theory of mind tasks. And this is something that we thought was completely impossible to solve using language models just a couple of years ago. What they show in this paper, or what Mikael shows in this paper, is that more recent models apparently can solve these tasks. So I'm going to quote from this. So models published before 2020 showed virtually no ability to solve theory of mind tasks. But however, the most recent version of GPT-3, so DaVinci 3, solved 90% of the tasks, and GPT-4 solved 95% of the tasks. This is really interesting. What is going on here? So if you look at what has actually been going on with the GPT-3 models, and this is a nice flow chart by Yao Fu, DaVinci 3, you see down there, It's not only a result of pre-training, but it's also a result of instruction tuning, supervised, and also reinforcement learning from human feedback. So something is going on when we actually fine-tune these models. It gives them a capacity to solve tasks that are really interesting. And of course, there was this paper from Microsoft Research, like last week or something, Sparks of Artificial General Intelligence, early experiments with GPT-4. And in this paper, the only thing they do is just test the API and solve tasks using the API. And they have some quite lofty claims about the capacities of this model. And of course, this contributes also to the recent debate about GPT-4. I'm not going to comment on the manifest that was published, but I'm just going to say congratulations to all of you, because these are exciting times, and you're really part of a very interesting development. Okay, so enough about the background. Let's talk about the work that we have done, GPT-SW3. And please don't misinterpret this slide. I'm not claiming that we have built a sentient model or that this model is an AGI. But I think if we meet again in 10 years, we might look back at this development as being actually the first steps towards something more general. So this is the perspective that at least we have. Now, another thing, if you have actually read the technical notes for GPT-4, you might have noticed how many people were actually involved in building that model. I think they have like 3 pages full of names that have contributed to that model. By comparison then, in our team at AI Sweden, the Natural Language Understanding Research Group, we're 10 people. So that's a very small team to build something like this. So what we have done is we form partnerships and collaborations with other people and organizations that think that this is a good idea to build something like this in Sweden. So we have competence in my team, but when we started this 1.5 years ago, we didn't have any data, we didn't have access to sufficient infrastructure to train models. But so what we have done is form these collaborations. So we work closely together with RISE and the NLP group there as part of the core technical team. We have had really good support from NVIDIA and especially Zenodya, who's talking, who might be here somewhere. We've also had really good collaborations with WASP, and in particular the Research Arena for Media and Language, and the National Supercomputer Center at Linköping. And I'm going to come back to those parts later. We also try to sort of promote a community, much like GAIA is doing. So we have a Discord channel called the AI Nordics. I know that many of you are part of this, but if you're not part of it, do sign up or just go there. Mail me if you don't have the link. So we try to build a community in the Nordics where we can collaborate on building good stuff and sharing information and papers. So by doing this, we get access to infrastructure and we have the competence, but the main problem is how do we find enough data to actually train a large language model in Swedish? So we're going to need to have like 300 billion tokens of data. How do we find that in Swedish? So we thought that we would be able to just find this in some data repository, which of course was not possible. So we started the data collection initiative about a year ago or something, and we spent more or less 6 months just collecting and processing data. And we have collected something we call the Nordic Pile, and that consists not all of Swedish data, but of Norwegian, Danish, Icelandic, also some English, and some code. And the reason why we're going for the North Germanic languages is because Swedish is typologically very similar to these languages. And we think that this variation would be beneficial for the model capacity. And also it gives us more data, of course. The way that we have produced the Nordic Pile, and there is also paper out now that you can read about the details, it's an archive, is we based more or less all of the data on existing corpora. So mostly derivatives of common crawl, like Oscar or MC4, but also other open sources. And I'm going to show you a breakdown of the sources in a little bit. And then once we have collected all the data, we of course do some processing of the data. We're not going to go into detail about this, but We can say that first we do some quality filtering. So we remove data that is obviously not good language, and we base the quality filters on several heuristics inspired by the literature. Then we go through several steps of deduplication to make sure that we have not identical or near identical documents in the data. So we do exact deduplication, we do fuzzy deduplication, and then we arrive at the final training set. That is sufficient high quality and sufficient variation. We then more or less arbitrarily weight the different data sources, just according to what we sort of think that the model will be used for. And then we have the final training data set. So we take a sample of that and train our tokenizer. And we opted for a sentence piece tokenizer with a vocabulary of 64,000 tokens. Now, if you work in the field, you notice this is slightly bigger vocabulary than normally you would use. Around 50K is sort of the standard. So the reason why we went a bit higher is because we wanted to have a little bit better representation across the languages. So for Icelandic, for example, we needed to extend the vocabulary. But it's a trade-off, right? Because if we use too large vocabulary, our embedding matrix will be huge, and that will affect performance. So it's a trade-off between representativity and efficiency. And this is a breakdown of the data sources. We don't have time to go into detail, but you can notice the different categories. So we have some articles, some collected from the Pile, like Archive and PubMed. If you've written a dissertation at the Swedish university, chances are your dissertation is in the data, because we use DIVA, where most of the universities in Sweden have uploaded their student dissertations. We have some books, we have some code, we have conversational data, and this is the place where people usually ask us questions. Why did you include flashback in your training data? It's because we want to model the language distribution, so we need lots of data, right? We have some task-related data sets like maths, summarization, maybe some question answering data sets, and then we have a lot of just web data, web scrape data from common crawl, basically, various derivatives. So at the start, we had 1.5 terabytes of raw text when we had collected data. Then we go through the processing steps, quality filtering, exact deduplication, and fuzzy deduplication. And then we end up with a data set of 1.2 terabytes of clean and nice raw text. So the breakdown for the final weighted training data sets across languages looks like this. So we have about 36% Swedish data with a nice variety of different sources. English is also quite a nice variety of sources. Of course, for the smaller languages, we don't have sufficient variation across categories. We take what we have. For Icelandic, we basically only have the GigaWord corpus, for example. And then we opted for 7% code in the final training data set, and that's completely arbitrary. But that means that we end up here when it comes to the Nordic Pile. I think it's like 380 billion tokens in total. So it's enough to train a big model. It's slightly more than GPT-3 was trained on, slightly less than Bloom has been trained on. And these are the model sizes that we have trained. So ranging from very small, tiny model with 126 million parameters, it's a tiny model, up to 40 billion parameters. This is just a breakdown of some hyperparameters across the models, and also the amount of compute you need to actually train these models. When we started the GPT-SW3 project, we were actually aiming for a 175 billion parameter model at the end, but we have now taken the decision to not train that because of recent developments in the field. We think that it's not motivated to spend that amount of compute training a larger model, because we think we can get more performance increase by going back and working on data at this point. But so the 40 billion model is probably the one that you should use if you want to build stuff on these models. Just as a nice example, if you would only have one A100 card and you would run max throughput on that card, it would take you more than 9 years to train the 40 billion model. So obviously we can't wait for 10 years to train our next one. And that's the reason why we use this one. It's Brazilius. It's our only supercomputer for AI in Sweden. It's a wonderful resource, donation from Knut and Alice Wallenberg Stiftelse. It's currently, or soon, will consist of 94 A100 nodes. It's being extended as we speak. So the new nodes, which are 34 new A100 nodes, they will have the larger cards, 80 gigabyte version. The old nodes, which are 60, have the 40 gigabyte version. We have had the luxury of using a third of the cluster for training our models, which has been great. It doesn't take 9 years then, it takes a couple of months for the big one. And quite importantly, this is a superpod, which means that not only is it DGX systems, it also has the InfiniBand networking between the nodes, which means that you can distribute your model efficiently. And this is where we have had really good support and help from NVIDIA. We've also used the Megatron software stack to train our models, and we've had great support from the Megatron development team, and Synodja, if you're here somewhere, has been really helpful in doing this. And it's been a pleasant experience for us. We've not experienced any major hardware failures during training. I think we only had like 2 node dropouts during training, and no big divergence spikes during our training. And the loss curves look really smooth and nice, which is good. And the models seem to behave as you would expect based on scaling behavior. So you go bigger, it becomes better, right? And you can actually predict the loss that you will end up with based on scaling loss. So we knew more or less exactly where we would end up with for the 40 billion version. So that's great. So we have a series of models now that we have trained. And the way that we have tried to put them out there is following careful and trying to be responsible when it comes to releasing these models. So right now we're doing something we call a restricted pre-release of the models. It's been available since January, and it means that you can get access to the model weights, you can download the entire model, but you need to fill in a form and you need to comply with the responsible AI license and things like that. So you can find everything on our homepage at AI Sweden, and all the models are available on Hugging Face at our repo there. If you look internationally at models, generative AI systems that are out there, you can see GPT-SW3 is up there in a blue box. Blue are models that are downloadable under some form of license. The green ones are models that are completely open source. And this is a compilation that has been published by Hugging Face, by the way. So you can see there are not a lot of models that are completely open. We would like to go there with GPT-SW3 and publish the model as complete open source. We hope to get there, but it's a complicated process, and the recent discussions in the field don't help in this process. So we're trying to be careful and responsible in the way that we share this. So right now, we're also trying to see if this model is actually useful. So, I mean, we know that it behaves good when it comes to language modeling, but can we actually use it to solve concrete tasks? So we have started something we call a validation project, being funded by Vinnova. And the idea is to provide an API and provide the models as they are, and to see if people can actually build useful applications based on this. And in the project consortium, we have actors from private sector, both small and large companies. We have actors from public sector, so government authorities, and we also have academia involved here. And we have a nice collaboration with CGIT, who I know is here somewhere. So we rent a DGX system from them to actually host our models. And so we have an API solution for this project. And I think that running inference even on our bigger models is quite fast. So we use 3 A100 cards to run inference on the bigger model, the 40 billion one. Nice, runs smoothly, but we don't have much traffic though. Right, so we are there. We have trained a model now on billions of tokens using billions of parameters. We have included some multilinguality in the model, of course, the North Germanic languages. So I think that we are more or less done with GPT-SW3 by now. We're doing one more iteration over all the models to produce instruction-tuned models. So it's going to be Instruct GPT-SW3 is going to be available in a couple of months. But that's probably it for this development cycle. And then we're going for trillions of tokens of training data. We might go slightly bigger on the model sizes, but especially we're going to look at other types of training objectives. So including more multimodality. We think that's really interesting. We're probably going to look more into data augmentation, like instruction tuning, various forms of reinforcement learning, perhaps not using human feedback, but perhaps using AI feedback. And also the possibility to include tools and things like that in the training. I think that's really interesting. So these are our plans, but of course, as you are all aware, it's a hectic environment there, and even if we make plans for what we think will be the next development cycle, we need to stay agile because of all the development that goes on. So these might all change in half a year or something. And we'll see where we end up, but it's going to be exciting times. And by that, I think I'm done with the presentation.
So we have time for a couple of questions. So one of the benefits of being on stage is that I can start with the first question. And I think one thing that I've always been thinking about is how big of a deal is funding? I mean, is money an issue here?
Yeah, it is. Yeah, it is. I mean, so the reason why we were able to build GPT-SW3 is because we are all we think this is the most fun thing to do in the world, right? The team. And then we have managed to find organizations that think that it's beneficial to support this in various ways. But if you compare this to international initiatives, it's a tiny thing that we have done. And the amount of funding that is going into GPT-SW3 is just tiny in comparison. And that's sort of where we are right now. We think that we will be able to build something really useful here in Sweden, taking the next steps, but it's going to require sizable investments. And it's important to sort of stress that. It's going to require sizable investments in infrastructure. So we have a training infrastructure. We don't have an inference infrastructure, for example. We're going to have to require lots of initiatives when it comes to data. And we are in Europe, so we need to be compliant to GDPR, which is quite challenging. And we need to have better funding for long-term major initiatives when it comes to this. So yeah, challenging.
So do we have one or two questions in the audience? I have light in my eye, so I don't really see if anybody is raising their hands, but if there is. Yeah, we have one over there.
So how does the model compare to ChatGPT when it comes to the Swedish output?
Yeah, so ChatGPT is one of the models, if you remember the flow chart, it's sort of in the middle in the flow chart. So that's not only a pre-trained model, it's also a fine-tuned model. And GPT-SW3, by comparison, is only a pre-trained model. So it's not been instruction-tuned, it's not been reinforcement learned, it's only a model that can play language games without instructions. So it doesn't compare at all to ChatGPT. Not function-wise, not training data set-wise, not the size of the investment.